In this video, we are going to talk about what a separable differential equation is. So let's get right into an example to motivate this. Let x be a function of t, which satisfies dx dt equals x squared times t squared. And I want to find x. So x is some function of t, and I'm trying to figure out what this function is. It's a function that when you plug it into this equation, it should satisfy it. So its derivative should equal x squared times t squared. We saw the idea with separating variables in the last video. I want to get all the x's on one side and all the t's on the other. So maybe I would multiply this dt over the right and then take this x squared and divide it over the left. So to divide by this x squared, I notice that there's a problem if x is 0, because we'd be dividing by 0. So let's consider that case and the case when x is not 0 separately. If x is 0, I have a specific value for x, it's 0. So I can just check, does that satisfy this differential equation? So let's look at both sides. So if x is 0, and I look at dx dt, its derivative, well, the derivative is 0 of 0 is just 0. What about if I plug this into the right side? X squared times t squared. If I plug in 0 for x, I'll get 0 squared times t squared, which is 0. So both sides end up being the same thing, which means that this works. So x equals 0 works. It is a solution to this differential equation. All right, but we might have other solutions in the case when x is not 0. In that case, we are going to be able to divide by the x squared. So let's do that. So I'll get dx divided by x squared. And then if I multiply dt over the right, I'll get, equals t squared times dt. Now that they're separated, I can do the integral on both sides. Okay, and on the left, well, this function is just x to the negative 2 dx. So if I do a reverse power rule, for the antiderivative, I'll get negative 1 over x. On the right, I'll get t to the third over 3 plus c. We've seen in the last video, actually, that technically there's a constant popping out on both sides. So that there's a plus c on one side and maybe like a plus d on the other. But I can move all the constants to one side, which would give me d minus c over here, which itself is a constant. So I'm just going to take this whole constant and just name it c. And that'll just be simpler. All right, so now let's multiply over the negative. So I'll get 1 over x equals negative t cubed over 3 minus c. Then I can reciprocal both sides. So I'll get x on the left equals 1 all over that negative t cubed over 3 minus c. All right, so we got this answer. So there's a couple things I want to notice about this. So it depends on c. So there's infinitely many solutions. There's an infinite number of solutions because there's infinite choices for c. Infinite choices for c. So we're not just getting one solution, we're getting infinitely many solutions. How could I check whether this actually works? Well, we could take it and plug it into this equation on both sides and see if they're equal. So let's do that. I got to take its derivative. So to do the derivative, I can move this whole denominator term up to the numerator, and that'll make it have a negative 1 power. And in the parentheses, I just keep it as it is. And now when I do the derivative, I got to do chain rule. So I deal with the outer part, the power first. That'll come down. And I'll get that negative in front, big old parentheses. Now the power is negative 2. And I keep the inside stuff as it is, negative t cubed over 3 minus c, times the chain rule step. The derivative of the inside is just negative t squared. So to simplify this, I notice that there's a negative here, there's a negative here. Those two negatives will cancel to make a positive. And let me just write the t squared first. And then this other term that has this negative 2 power, let's rewrite that as 1 all over that parentheses thing to the positive 2. So negative t cubed over 3 minus c. And actually, since I have this positive sign in front, I could just get rid of that positive sign. Let me just erase that. All right, so what I have now is I have t squared times this fraction squared. But I notice that fraction is actually just x if I squared it. So this is t squared times x squared. And that's what we wanted. We've just shown that dx dt equals t squared times x squared, but that's exactly what my equation says. So this is a solution. So let's box it. Let's box it. So we have two types of solutions. We have x equals 0 here, and we have things that look like this. And both of those are solutions. All right, so let's give a more formal definition. So we say that a differential equation that can be written in the form dy dx on one side. On the other side, I'll have a function g of x times a function h of y. So the part with the x and the part with the y are kind of separated like this. This is called separable. This is called separable. When it is like this, I'll be able to move this dx over to the right by multiplying it. I'll be able to move this h of y over to the left by dividing it and get the y's and the x's on different sides. So not all differential equations are separable. Let's give an example of a non-separable differential equation. So one example is dy dx equals x plus y. We might look at this and be like, oh yeah, like on the right, this isn't just like the part with the x's and the part with the y's being multiplied together. They're being added. But, as we'll see in this next example, just because it doesn't have this form right away, doesn't necessarily mean I can't do algebra on it to get it into that form. With this problem, no matter how hard I try, it turns out I won't be able to do that. I won't be able to separate the x's and the y's onto separate sides. And I could try. In fact, I'd encourage you to pause the video and to try it. But, maybe what I could do is I could subtract the y to the left, and I'll get negative y plus dy dx equals x on the right. And now maybe let me try multiplying the dx over. So if I do that, I'll have to multiply this side by dx and the other side by dx. But on the left, that dx will distribute. So I will get negative y dx plus dy equals x dx's. So, when I tried doing this, I wasn't able to just get all the x's on one side and all the y's on the other. Because on the left side, I still have both x's and y's over here. It turns out that no matter what I do, I won't be able to separate this. It's not always immediately obvious whether an equation is going to be separable or not. We might have to try doing some algebra to help determine it. In our class, we're going to be working with examples where, with just a little bit of work, a little bit of thought, it'll be clear to tell whether it is separable or not. So let's look at another example. Let's say I want to solve dy dx equals y squared x minus y squared with this initial condition that y of 0 equals 4. So even though this right-hand side doesn't look like just like all the x's and all the y's in separate functions multiplying together, I can get it in that form. Because I can factor out a y squared on the right and then be left with x minus 1. And now, though they are being multiplied, a function of the y's and the function of the x's. So now I can separate this. Let's divide the y squared over to the left and multiply this dx over the right. So if I do that, I get dy over y squared on the left equals x minus 1 dx on the right. Just so that it's clear that this whole x minus 1 is multiplying the dx, let's put a parentheses around the x minus 1. And now I'm ready to take the integral of both sides. So integral of this side, integral of this side. We just saw how to do this antiderivative on the left. That's going to be negative 1 over y. On the right, I'll get x squared over 2 minus x. And then I got to put my plus c, my constant. There's one detail that you might have noticed that I've kind of glossed over, which is, I had to divide both sides by a variable. And in the last problem, I had to think about cases. What if that was 0 versus what if that's not 0? For this problem, there's an observation I want to make about that step and why I won't need to consider cases. So note the problem tells me that y of 0 equals 4, which means when x is 0, y is 4. So because y is 4 at this point, that means y can't just be 0 the whole way through, like in my first case in the last problem. So y isn't just straight up 0, since y of 0 equals 4. So we don't need two cases. We don't need two cases like in that last problem. So that's nice. Okay, that is going to cut down my work a little bit. All right, so let's solve for c using this initial condition. So let's use y of 0 equals 4 to find the value of c. So let's plug that in. On the left, I'll get negative 1 over, and y is 4, equals on the right, I'll get x squared, that's 0 squared, over 2, and then minus 0 plus c. And this just gives me that c equals negative 1 over 4. So I can take that value of c, plug it back into my equation here. So doing that, I'll get negative 1 over y equals x squared over 2 minus x minus 1/4. Now I can multiply the negative over. So I get 1 over y equals negative x squared over 2 plus x plus 1/4. And reciprocal both sides. So I'll get y on the left. On the right, I get 1 all over this whole thing, negative x squared over 2 plus x plus 1/4. And we got it. This is a solution to our differential equation. I won't check this one and whether it works or not. I'd encourage you to do that for practice to see like, oh, if you were to plug it back in, is it going to satisfy this? But it turns out it does. All right, so let's take a look at another example. So now let's say I want to solve y prime equals e to the 2x over y with initial condition y of 0 equals negative 3. So y prime is just another way to write my derivative, dy dx. And I can isolate my variables by multiplying this y over to the left and multiplying this dx over to the right. So that'll give me y times dy equals e to the 2x times dx. One kind of important thing that I want to mention is before we take the integral on both sides, we need the dy and the dx to be in the numerator. Like, it doesn't make sense if I'm doing the integral and I have something like, for example, like 1 over y dy like this, like where the dy is in the denominator. That doesn't make sense in the context of an integral. So I need the dy and the dx to be in the numerator. All right, so if I integrate both sides, on the left, we'll get y squared over 2. On the right, that antiderivative is e to the 2x. And then there's a constant that should pop out in front because, to check this, if I did the derivative of e to the 2x, I just get e to that stuff times the derivative of that stuff, which pops out at 2. But I don't want that 2 to pop out. There's no extra 2 here. So to cancel out that 2, in front of this, I would need to put a factor of 1/2. All right. And then I got to put my plus c. There are two common ways that we can go about solving for this constant in terms of the order in which I do it. In the first way, I'm going to just solve for c right away, just like we did in that last example. So now let's use this initial condition. So if I use that and I plug that in, we're going to get negative 3 is the value of y squared over 2. So I'm plugging that in for the y. On the right, I'll get 1/2 e to the 2 times 0, and then plus c. Nice. And if we simplify this, we get 9/2 equals 1/2 plus c, because e to the 0 is 1. And rearranging this, I get 4 equals c. So let's take that value of c and plug it into our equation. So I will get y squared over 2 equals 1/2 e to the 2x plus 4. Now I can multiply over the 2. So y squared equals e to the 2x plus 8. And square root both sides. So I'll get y equals big ol' square root of e to the 2x plus 8. But anytime I square root both sides, I got to put a plus or minus in front of the square root. So how do I know if it's the positive square root or the negative? Well, it's based on this initial condition. So since y of 0 equals negative 3, if I were to plug that into this equation, here I'll get e to the 0, which is 1, and I'll get the square root of 1 plus 9, which is 3. So for that to end up equaling negative 3, because I need y to be negative 3, it's got to be a minus in front of the square root. So that's how I know for this problem that it should be, y equals negative in front of my square root, e to the 2x plus 8. And that's my answer. That is my function y that satisfies this differential equation. So there's another way I could have solved for c, which is just doing things in a slightly different order. I could instead isolate for y first. So if we did that, and I multiplied by 2 first, I'd get y squared equals e to the 2x plus 2c. Now I could square root to get y equals plus or minus big ol' square root of e to the 2x plus 2c. Next, let's use that initial condition. Use the fact that y of 0 equals negative 3. And if we were to use this, and plug that in, what I'm going to get is negative 3 on the left equals, and I'll think about if it's a plus or minus, I'll get my square root, and inside of it, I'll get e to the 0 plus 2c. Well, when I work out the square root of something cannot end up being negative. I can't get a negative number out of the square root. So the only way for this right-hand side to end up being negative 3 is if, for this plus or minus in front, if it's a negative in front of the square root. Okay, so that's very similar reasoning to what we said here for why it was a minus in front of the square root. All right, so let's multiply both sides by the negative now. So 3 equals square root of 1 plus 2c. If I square both sides, I get 9 equals 1 plus 2c. And then if I subtract the 1, I get 8 equals 2. Actually, let's just do 2 steps in one. Let's subtract 1 and divide 2. So that'll give me c equals 4. Nice. And then I can plug that back in to my equation once I had this y isolated. So that will give me y equals, now I know it's a negative in front of the square root, and square root of e to the 2x plus 2 times c, that'll be 8. And we got it. We got our answer. The same thing as before, just doing things in a slightly different order. All right, so let's end the video with one final example. Now let's suppose I want to find a curve where at any point the slope is always the product of 4 and the x-coordinate and the y-coordinate, okay? And it passes through 1, 2. All right, so we have this word problem. So let's start to break this down. The first thing that I want to do is find the key verb that's going to help us translate this to an equation. And that's is. Is means an equal sign. So before is, it says the slope. Slope is derivative. So slope is, that is my dy dx. So it's saying the slope is the product of, that product means I'm multiplying a bunch of things. So product of 4 and the x-coordinate and the y-coordinate. So that's what I'm multiplying together. So the product of 4 times the x-coordinate, so that's x, and the y-coordinate, y. And I got my differential equation. We also have this initial condition that y of 1 equals 2. So now let's solve this. Let us solve this differential equation. So at this point, I want to have you do a quick pause for about 2 minutes, maybe 3 minutes, and see if you can separate the equations, separate the variables, here, and integrate both sides. So pause it in 3, 2, 1, and try that. All right, so hopefully you did that. Let us go ahead and do that now. So I'm going to divide the y over to the left and then multiply the dx over to the right. So that'll give me dy over y equals 4x dx. Now I can integrate both sides. On the left-hand side, I'll get natural log absolute value of y. On the right, we get 2x squared, and I got to put my plus c. So now let's do this. Let's do this second strategy way, which is let's try to isolate the y for practice and then solve for c at the end. So, okay, I have this equation. I want to try to isolate the y. So I can transform this log equation to exponential form. Because of the base of the ln is e, so this would be e to the 2x squared plus c power equals absolute value of y. The other way I could see that is if I did e as the base on both sides, on the left-hand side, the e and the ln would cancel, and on the right-hand side, I just get this. And that's exactly what we have here. So those are two equivalent ways of thinking about this. All right, so we have this. Now I need to get rid of the absolute value. So there's something I want to remember about when we do something like that. If I had something like absolute value of y equals 6, then y could be two things. It could either be 6 or it could be negative 6. So it's plus or minus 6. Similarly, if I get rid of this absolute value, I'll get y equals plus or minus this thing. And let's just do some exponent properties on that to write it as e to the 2x squared times e to the c. Okay, in fact, I like to put this e to the c first. So let me move it around. Let's move it around and I'll get that e to the c in the front. All right, so nice. The next thing that I notice is e and c are both just numbers. They're both constants. So even including this plus or minus, this whole thing in front is just a constant. So let's rename it. Let's let this be k. I'm going to rename it as k. So we're getting y equals k in front and then e to the 2x squared. That just makes it a little bit simpler. So now when I use my initial condition, so now I'm going to use the fact that y of 1 equals 2. So if I plug that in, y is 2 equals k times e to the 2, and it's 1 getting squared, 2 times 1 squared. So if I isolate for k, we get that k equals 2 over, this is e squared. All right, so I can take that value of k and plug it back into my equation for y. So doing that, I get y equals, k is 2 over e squared times e to the 2x squared. It's totally fine to leave my answer like this. Just for practice simplifying this, if I have e to a power divided by e to a power, I can use my exponent properties to subtract the powers. So I'll get y equals 2 times e to the 2x squared minus 2. And that's just my final answer, simplified. All right, and there we have it. So in our next video, we are going to do some more practice with these differential equations, and we're going to look at examples that involve exponential growth and decay.